favorable at lower temperatures. Now, why does that, what happens with that? This is negative. At a low temperature, we said that minusing a negative value makes this positive, okay? And so it will always be positive, but at low temperatures, it will tend to only subtract a small amount from this. It'll still be, what, negative overall. As temperature increases, we have the possibility that eventually this becomes positive enough that it will be a larger positive number than this is, and our reaction will become non-spontaneous. Okay? Alrighty, so now we're going to switch this to an endothermic process. And we're going to go back to a positive for this. And again, it depends on the relative magnitudes of delta H and delta S. It's more favorable at higher temperatures. Remember, what do we want? We want a negative. If this is positive, this has to be a high enough temperature that this becomes bigger than this is, so we can end up with a negative value and have a spontaneous process. Alrighty. Last case, where we have an endothermic process and we have a negative process. And here we have this case where it's not spontaneous under any conditions. Alrighty. And you will be asked to analyze what the driving force is. And so in this particular case, where you have an exothermic process and you have more order, you would say that the fact that you have an exothermic, the enthalpy is the driving force. Why? Because this is the part that's what causing it to be spontaneous. Okay? Okay. So we've already pretty much talked about this. We have our S of our universe. We said that we could fill in for our surroundings. We have our change in entropy for the system. We multiplied through by negative T. And so this is just, again, we're going to take this part and relate it to the change in free energy. And when we say free energy, we mean that how much energy is there to do useful work. If we can take a look at how the system changes by looking at the entropy change, we take a look at the surroundings by actually looking at the enthalpy of the system. So this is nice. We've got variables that we can measure in our system, and we're going to recall that T, negative T delta S, we're going to say that that's represented by our change in free energy. And so under standard conditions, we have a standard change in free energy, which is equal to the standard change in enthalpy of our system minus T delta S of the system. This is just the slide that shows what I previously did on the board. So there's not really any new info other than that there's a very striking picture here of Mr. Gibbs. All right. But it was groundbreaking at the time. I mean, if you think about it, during this particular time period, chemistry was mainly a descriptive subject. And so there were just, this does this, this does this, this does this, this does this, this does this. And so they were trying to bring order. And so they realized that exothermic reactions did tend to be spontaneous, to be product favored, but not all of them were. So how are we can we get some kind of an idea about where we can tell for sure which reactions are going to be thermodynamically favored? And so relating both the enthalpy change and the entropy change is what makes that happen. All right, so the Gibbs free energy change is equal to the total energy change for the system minus the energy lost in disordering the system. If reaction is exothermic, meaning that energy is dispersed and the entropy increases, then and matter is dispersed, then the standard change in free energy must be negative. This is just another way of thinking about it. We looked at it in terms of negative and positive signs, and now we're looking at it in terms of energy dispersed and matter dispersed. The reaction is spontaneous and product favored. We're just summing up all our, so this is just the same as the chart. If the reaction is endothermic, meaning we have a positive H, entropy decreases, then delta G must be positive. The reaction is not spontaneous. Notice that in the situations where we have opposite signs, those are always the ones that are either all spontaneous or not spontaneous at all. It's the ones where you have both positive and both negative, where you have to learn what the temperature dependence is. Are they going to be more likely to occur at lower temperatures or higher temperatures? So that's another way to look at it. Oops. All right. We've already pretty much gone through all the different possibilities. If you have any questions, you can ask me about that. When you have exothermic and the entropy value decreases, it depends on what the temperature is. Again, if you have an endothermic reaction and the entropy changes, it increases, that would also be temperature dependent. You should also be able to convince yourself of which temperature dependence is it a situation where it is going to be more likely to be spontaneous at a lower temperature or a higher temperature. Okay? All right. There are two methods of calculating our standard change in free energy. The first way is, you can imagine, since we've gone to all this trouble to come up with this equation, we can determine the change in our standard enthalpy, we can determine the standard entropy, and we can use the Gibbs equation. Sometimes you'll be told to use tabulated values by tabulated values, or if somebody tells you to use standard free energies of formation, that means to look up a table in the appendix. So those are the two ways. If we use tabulated values, this is the way we do it. It's the products minus the reactants. Again, remembering that for Gibbs free energy, it's a state function. We postulate that all the elements in their standard state have a free energy of 0. We combine those elements, we get products, and that's where we get the standard formations. Whenever you have an element, you will not be given a Gibbs free energy for it, and so you will just have to supply to yourself the fact that